Hi, today we're gonna solve the last challenge from ROP Emporium series. It is called ret2csu. It is very similar to the ret2win challenge we already saw. We again have to call a ret2win function, but this time we have a constraint on the RDX register, which must contain a specific value, and we have very few gadgets to populate this register. Furthermore, some entries of the PLT table are tempered, so we can't just call functions from PLT. To bypass these limitations, we're gonna use a technique called ret2csu. So let's start playing with the binary. It is a 64-bit binary. Let's check the mitigations which are in place. We have no canaries and the code is not position independent. So let's run it. We can try to exploit it exactly like we did for the ret2win challenge and see where our exploit gets broken. We create a cyclic pattern. We provide it as an input for our program. We get a segfault. We dump the core file and we analyze it. We then look up the value on top of the stack, which is the overwritten return pointer. So we need a padding of 40 bytes for our payload. We then retrieve the address of our ret2win function. And we start crafting our payload. So 40 bytes of padding. And then the address in a little endian encoding. The program crashes, but before it tries to execute a command, which is meaningless because the constraint on RDX register is not satisfied, of course. So let's analyze with the radar why this happens. We analyze the binary and start by decompiling the main function. This simply calls the pawnme function, so let's decompile it. Here we can see the PLT tempering. Here is the vulnerability. Let's decompile the ret2win function. We can see the call to the system function, but it's better to disassemble the function to understand what's going on. Our magic value is copied into this variable, which is then used to XOR some values, so probably the command is just encrypted and it uses this value from RDX to decrypt it before execute it. Now we can search for some ROP gadgets to manipulate RDX. And this last gadget is not a random one, but is part of the libc-csu init function, which gives the name to this technique. So let's analyze it. Here is the move gadget, and we can also see another useful gadget which allows us to set a lot of registers. Some instructions are not shown in the disassembly listing, so let me just disassemble all the instructions. Then this call instruction is executed, so we can call an arbitrary function whose address is stored somewhere in memory. Since the ret2win address is not in memory, we don't have an easy way to write it somewhere. We instead gonna try to find the valid function for which we have a pointer and do side effects want affect RDX, RBP and RBX. A valid pointer for our goals is stored in the dynamic section. You can see we have pointers to init and fini. So let's disassemble the init function. This simply creates some space on the stack, reads a function pointer, and it calls it if it's not null. Then it simply restores the stack and returns. So now we have all we need to craft our exploit. We can extract the gadgets from the binary. Then we spawn a process and we just send some random test input. Then receive all the data until the end of file and we close our pipe. Our ROP chain will begin with the pop instructions. We have the address of the pops gadget. Then we need all the values to populate the registers. RBX is used as an index inside the table of function pointers. So we can put the value 3, which is the index inside the dynamic section for our pointer to init. RBP is subject to a constraint due to these instructions, so it must have RBX plus 1 as value. R12 is the address of our table containing the pointers, in our case dynamic section. R13 and 14 are useless for our purposes since they control the values of RSI and ADI, so we can just put 0. And finally we put the magic value we need into RDX in R15. Then we have the address of the move gadget. Let's go back to the libcsu disassembly. When the executioner returns from the int function, it will perform the check on RBX and RBP, and then it will move to the last part of the function, which simply adjusts the stack. So we have to put the 8 bytes word in our option. And finally the ret2win address. Our payload will simply contain this ROP chain plus a padding of 40 bytes. Let me save the payload into a file so that we can later use it to debug our exploit. And let's replace this with our payload. And we are ready to run our exploit. It works, we get the flag. So let's use the input file we just created to inspect the execution of our exploit. We put a breakpoint on the return instruction from pawn me function. So the ROP chain starts with the pop instructions. These populate our registers. Then we go to the move gadget, which sets RDX to the desired value. Then we call init function, which does nothing essentially. And when we return, the check on RBP and RBX is performed. The last series of pops is executed. We finally jump into ret2win, and you can see that RDX still holds the magic value. So we just need to continue the execution to get the flag. And that's all for today.